Hello, my name is Kang Chen. My presentation is titled Towards More Accurate and Trustworthy BEV Occupancy Grid Prediction. Under this theme, I have completed two major works, PriorMotion and LegoMotion, both of which have been finalized, submitted, and are currently accepted at major conferences. I'm Kang Qian, a second-year master's student. Today I would like to share the PriorMotion, which is accepted to the ICCV Special Environmental Perception and Cognition from the Foundation for Decision-Making Intelligent Agents. Computer vision serves as the key enabling technology, while initially focused on image classification. The field is rapidly evolving. Professor Fei recently introduced the concept of spatial intelligence, where spatial refers to environmental perception intelligence, I suppose, and refers to recognition. This is critical, as demonstrated by models by Voxposa in robotics and crucially for autonomous driving by UniAD, the CPR 2023 past paper, but which use occupancy grids for trajectory planning and collision avoidance. Traditional perception paradigms often object level. This involves a cascade system of 3D detection, tracking, and motion prediction. While offering stable motion features for unknown objects, this approach suffers from error accumulation and critically fails to detect unknown obstacle categories, leading to potential downstream task failure. Inspired by robotic occupancy grids, grid-level methods like BSD STI transformer predict properties for each grid cell in a bird's-eye view, which we call BV. This solves the open-world problem of detecting unknown obstacles. However, they often lack physical consistency, exhibiting issues like fragmented instance segmentation, poor motion stability, and degraded performance at long ranges where point clouds are sparse. Most paradigms have fundamental limitations. For object level, the cascaded structure lacks generalization to unseen objects, and bounding boxes cannot represent complex shapes. For grid level, the discriminative per grade regression paradigm is limiting, and the lack of instance-level reasoning harms consistency. To address these issues, I present two works. PriorMotion tackles the first limitation by incorporating generative modeling and motion field priors, significantly improving performance and generalizability. LegoMotion addresses the second limitation by introducing instance-aware interaction modeling and features enhancement, achieving strong performance with minimal parameter. Current grid-level methods struggle with spatial temporal consistency due to data sparsity. We find expression in the structured patterns inherent in BV flow ground truths, a dense representation acting as a prior. For example, vehicles moving straight have constant velocity. Turning vehicles follow smooth curves and semantics motion are constant within an instance. This leads to our core questions. Can structured prior knowledge enhance BV flow prediction? And how can we best represent and integrate this prior? In particularly, we find that providing FMCW layers, radio velocity channel, a strong motion prior to a baseline model like MotionNet drastically improves performance. This experiment directly answers our first question. Yes, prior knowledge helps. This motivates our goal, equating standard 3D data with similar prior enhanced capabilities. To propose PriorMotion, Generative framework models provide knowledge as a distribution for conditional sampling-driven inference. We move from a standard encoder-decoder to a generative architecture. We introduced the Raster-Vector encoder for RVP to extract multi-perspective priors from the motion field ground truth and the dynamic static prior generator, DSPG, to generate a prior distribution in latent space to guide the decoder. Our framework consists of 3 parts: a beam encoder for spatial temporal feature extraction from 3D LiDAR sequences, an RVP which learns to extract useful priors, and the DSPG which models task-specific distribution for dynamic statics. The prior knowledge is only used during training to learn these distributions. The decoder uses autograph design for motion prediction. The RVP extracts priors from both raster and vector perspectives. The raster branch uses CNN as attention to capture global and local spatial temporal patterns. The vector branch extracts instant-level representations and models their interactions, providing high-level relational clues in raster-level view might miss. They are fused into a rich prior view feature. The DSPG module separately models prior distribution for static dynamic things elements, acknowledging that we perceive them differently. It uses VAE to model spatial distribution for the state estimation and cell classification tasks. Crucially, for motion, it employs an autographic process in latent space to generate future motion priors, capturing temporal dynamics and interaction. We evaluate extensively on the popular nuisance data set using the standard split. To further validate generalization, we also use a dataset connected with an FMCW ladder using our own car. Our experiments aim to answer: does PriorMotion improve motion semantic projection? Does it enhance generalizability, long-range performance, and motion stability? To quantify generalization, we propose a masked evaluation protocol with hold gradient updates for a specific object category during training, and then evaluate performance only on that masked category at test time, simulating an open world scenario. To thoroughly evaluate these aspects, we propose new metrics specifically targeting generalization capability, motionability, and long-range displacement error, providing a more complete assignment of BB flow prediction. When integrating PriorMotion onto state-of-the-art backbone TVN SD transformer, we observed significant gains in the motion prediction metrics. Conclusion 1. Our method improves the range degree, the prediction error across different backbones, and another conclusion is that the incorporation of prior knowledge provides more significant gains for dynamic objects. PriorMotion also shows substantial improvements on our newly proposed metrics for long-range perception, motion stability, and most importantly, generalization. The increased radiance of the cycle visually represents the gain in generalization. Notably, our framework can enhance a weaker backbone to perform competitively with a stronger one on generalization. PriorMotion achieves the highest semantic segmentation accuracy for 3 out of 4 foreground classes, with performance on par with the SOTA on the remaining classes. It achieves the highest mean class accuracy, improving over motion as by 8.5% and BSDF by 2.0%, despite using a simpler backbone and fewer tricks. Ablation study confirmed the contribution of each component. Both the vector and raster parts of the RVP improve motion prediction for slow and faster moving grids, but can slightly hurt static performance. The DSPG's dynamic static modeling effectively mitigates this issue for static cells. The autographic generative decoders significantly boosts the performance of fast-moving projects. Visualize clearly demonstrated improvements compared to the baseline. Based on our PriorMotion predicts are closer to the ground truth. We observe more coherent instance segmentation and significantly improved motion vector consistency, especially for turning and distant regions. On nuisance, PriorMotion shows superior performance with more and more results here. On the FMCW benchmark, the advantages are also evident, particularly in challenging scenarios involving extremely high speeds and sharp turns, where prior knowledge of motion patterns is most valuable. Thank you for your attention. I welcome any questions and feedback.